Okay, so I'll start the recording. Okay, good evening again for all of you. If you registered lately for this Zoom session, so today we will talk about balanced binary trees, which means they are binary trees, but they have this very interesting property that after you insert something there, the tree will change its structure. It will still be a binary search tree, but it will try to distribute an even number of values on any right and left side of each node. Okay, and this will increase the complexity of insert because all the other operations which are specific to binary search tree are the same. Okay, so let's create a new project for today's example. And before diving into the project, let's try to visualize the problem with the binary search tree and why we need this kind of balanced tree. Okay, I will put the link in on Zoom chat if you want to see that for yourself. Okay, so this is the visualization for binary search tree, and here I will have the visualization for AVL. Okay, now the problem with the binary search tree is this one. If you get the values sorted, or most of them are sorted, somehow you have a process that delivers you those values in a sorted manner. So for example, you get 10, okay, and after that you get 20, okay, and after that you get 40, okay. You see, each time by doing the same logic that we covered, always check the new node value or the new key value with the current nodes, and after that you search a location for that new key by moving on the right or on the left, depending on the relation between the new key value and the current node. Okay, so you see, by passing values which they have this, let's say, particular property that somehow you get them in a sorted manner, okay, the tree will grow on a single direction, like on a diagonal. And the problem is now that this is actually a list. It's a simple linked list. So it will have the same efficiency for searching as a simple linked list. But you have a more complex structure because it's a binary search tree. So instead of having only next, you have right and left. Okay, so binary search trees, they are vulnerable to this kind of scenarios when the values somehow they are inserted into the tree and they are in an order. Okay, they are, I don't know, ascending, they are sorted ascending or descending. Okay, so what do we need? We need a structure which will try to rebalance, which means if we want to have that optimal search complexity of logarithm base 2 out of n, it means that if I would redraw this binary search tree in order to distribute evenly on left and right all possible nodes, I will start, I think, with 40 here in the middle, and after that 20 will go on its left side, 10 here. So you see, we separated the values, and even we can improve that tree by rebalancing it again. So in order to reach that perfect complexity, logarithm base 2 out of n. And you can actually do that without knowing about AVL trees. How? You cross the binary search tree in order. Sorry, not in order, in pre-order, in order to get the value sorted. Remember, by crossing the tree in a pre-order fashion, you get all the keys sorted ascendingly. So you get it's easy to get all the keys sorted. And after that, using something which is very similar to binary search, each time splitting the interval in two, you insert the keys again, and you always insert the middle one. So you can actually do a rebalancing of a normal binary search tree, but that will take time. Just imagine that after you insert a key, you cross the tree, get a list, a sorted list of keys and using something similar with the binary search by taking always the middle value of an interval, inserting it again in a tree. So this is very costly. So we need something which is more efficient. And that's why you have balanced binary trees. And AVL is one of them. Red and black, it's another one. Okay, so let's try to insert the same values as here, 10, 20, 40, 50, 100. Let's see what will happen. So 10. Now this is an empty array. And you see each time when we insert a node, there is this value attached to a node. And this is something we need to compute. And this is a balance factor or a weight. And you will understand why we need that value. So after that, let's insert 20. Okay. So you see up to this point, everything's okay. But here, when we inserted a new value, because now 10 has a sibling on its right side, its balance factor or weight, it's 2. Okay, and the new node balance factor is 1. So in this approach, they are counting the levels of each node. So for example, here, they are counting the current level. So this is level 1. And because we have a child node on the next level, this means the weight or the balance factor of this node with 10 is 2. And this is actually a difference between the size or the height, this is more correctly, the height of the right side subtree minus the height of the left side subtree. So what's the height of the right side? Now you see they are counting also the level on which you have that node. So that's why the height of the right side subtree is 2, 1, 2. Now, what's the side or the height of this right side subtree? It's 1 and nothing there. Now, in our implementation, we will not count this level here. Okay, so we will say the current node is on level 0, and we count only the levels downwards. Okay, so in our approach, this will be 1 and this will be 0. Okay, but this is a visualization for this university. So this is how they compute it, but it's the same rule. Now, this is just a detail, will not influence the algorithm. Now, let's add 40. Let's see what will happen. Okay, so you see 40 is inserted normally. So the insert algorithm is similar with the one from normal binary search trees, but after that, after they inserted, let's do that again, and I will keep pause. Okay, so you see, they inserted a new node here, and this is normal. We know how to do that. And now, when they go back towards the root, they will recompute the balance factor for each of the nodes on that path. Okay, it's the same path from root to the location where we inserted 40. Okay, so let's see. Now they will recompute the balance factor for this one, and it will be 2. Okay, you see. And after that, they move backwards again to the initial start point, which is the root of the tree. Now it will recompute the balance factor, and now it's 3. So you see, and visually, we can actually see that the tree is unbalanced because it has a lot of values on the right side and none on left. And by having 3 values, I think we can rebalance it by making this intermediary node the root node, moving 10 on the left side and keeping 40 on the right side. So you see, this is important because this is the place where we will rebalance the tree. It's the first node from the route backwards. So going back from the new node towards the root is the first node that will give us a value that will say to us, hey, now you have an unbalanced tree. So in their example, the value which we will search for in order to rebalance the tree is 3. But like I said, in our implementation, this node here will have a balance factor of 0, this will have 1, and this will be 2. So for our implementation, the balance factor or the weight factor is 2. This is where we will need to stop and rebalance it. So what they do, they find and this node is called a pivot, because generally we will do some rotations. And here, by knowing the values of these balance factors, so here is 3, 2, 1, and you see, because this value is always computed by height of the right subtree minus height of the left subtree, if the value here is positive, it means that you have more nodes. The height on that side subtree is bigger than the height of the other side subtree. And because the value is positive, it means here the height is bigger than on the other side and is visible. And because this is the first node that has that special value, which we will not accept, and like I said, here is 3, but for us will be 2 because we don't count the current level. Now, this is called a pivot. And what they will do a simple rotation to the other side of the unbalance. So because this value is positive, it means we have more nodes on the right side. So we need to rotate the entire tree on this pivot to the opposite side, which means let's rotate it to the left. Okay, so step forward. And now that node goes down on the left side and its right sibling goes up. And now if you recompute the balance factors, once again, we are, let's say, in normal values, which means any node here in a binary balance tree will have a weight or a balance factor of either 1 or 2. In this example, in our implementation will be either 0 and 1. And if all the nodes have that balance value, either 1 or 0, it means we have an AVL tree. Okay? Otherwise, after we insert a node, that's the reason for unbalancing the tree. When you go back recursively, recheck the balance factors, and the first node that you will find to have a balance factor 2, it means we need to do a rotation. Okay, and here you have actually 2 basic rotations. What you have seen here, it's a basic rotation to the left, and there is an opposite rotation, and after that there are 2 complex rotations, which are actually 1 rotation on one side and 1 rotation to the other side. So now we balance it. Now let's unbalance the tree on the left side. So I will insert 5. Okay, 5 goes here, 2, 3. Okay, now like I said, but they are not rebalancing it, even if this one. So let's see what's the height here. The height here is 1 and the height here is 2. Yeah, the values here are not, they accept only also 3, but this is how we will compute the height. So this is the root node, okay, or any node. Now, the height of the right side subtree will be in our case 1, because we have only 1 level here. The height of the left side subtree in this case will be 2. And now if you do the difference 1 minus 2, here you will have minus 1. So that's why it's okay. Now, they have a different approach here of computing the balance factor. And I don't like this part here. Like I said, in the end, the algorithm is the same. But in our perspective, this goes like this. Okay, so just me show you. This is how we will compute. I will just give you a brief example to understand why we will do differently. Okay, so let's clear the canvas. Okay, so let's suppose you have this tree. This is how we will compute. It doesn't matter the values here. It's a binary search tree, whatever. So we have some nodes here. Okay, and maybe here we have something like this. Okay, so like I said, in our implementation, we don't count the current level. So you have a level here. Okay, this is one level. You have a level here. We have another level here for these nodes, and this is the last level. So let's compute the height of different subtrees. For example, if you are here, what's the height of the left side subtree? So let's see, 1 level, 2 levels, 3 levels. So the height of the left subtree for this node, so let's say h height of the left subtree is, in our case, 3. Now, what's the size of the right subtree, the height of the right subtree? So 1 level, 2 levels, so it's 2. So the balance factor, let's say BF, okay, equals, and we can choose the way we do the subtraction, either right minus left, left minus right, it doesn't matter. The values will be in the end the same. Okay, so let's go for right minus left. So what's the balance factor for this node here? Let's see, is right 2 minus 3 is minus 1. Okay, now what's the balance factor for this node here? For example, the right subtree has a level, a height 1, only one level, and the left side is also 1. So the balance factor here is 0. Now, what's the balance factor for this node here, which is a leaf node? Is the height of the right side 0 minus height of left side is 0. So 0, this one has also 0, the balance factor. Okay, now let's see this one. So the balance factor of this node is what? Right side is 0, 0, minus, let's see on the left side, 1 level, 2 levels. Is 0 minus 2. So here you have minus 2. Okay, this is the balance factor for this node. For this one here is 0 minus 1. So it's not number of nodes, it's the height, how many levels downwards you can go. So once again, this is minus 1, and for this one here is 0. So this is how we will compute the balance factor. Now, every time in our philosophy, in an AVL tree, if the tree is balanced, so it preserves its AVL properties, all the nodes will have either 0, minus 1, or plus 1. Because every time we reach a situation when the balance factor is 2, it means we have an unbalance already because of an insert or a delete, and we need to rebalance the tree. So we will always try to keep each node in this factor. So every time we will try to rebalance it, okay? So try to see the other examples based on this perspective. I don't know, for me, it makes more sense like this, to compute them like this. But like I said, the algorithm is the same. So if I go back here, and let's insert another one, like 3. So 3 will go here. Okay, now the tree is unbalanced, and you see it's rebalancing it again by doing a reverse rotation. And now let's try to do one of the complex rotations, which means one rotation to one side and another rotation on the opposite side. So this is called the double rotation. So in order to reach that situation, I will insert, let's see, 15. Bigger than, okay, goes here, pause, okay. And yeah, let's see what it will do. You see, now it has recomputed the balance factor for the root node, which is 4. So in this case, it means this is quite unbalanced. But you see, at this point, you may say the unbalance is on the left side. But when you go here, the unbalance is actually in the opposite direction. So here, in order to use a simple rotation, we will use this trick. We will do a simple rotation like this, so to the left, in order to unbalance this subtree on the left side. And after that, we do a rotation here to the right. okay? So we want to have the same direction of the unbalance, okay? Because here the unbalance is on left side, but now it's on right side. Let's see how they do it, okay? So, yeah, but they do it in one step. Okay, so at some point it's okay with this visualization, but they do it differently at some point, the visualization. Okay, so the idea is to understand why we need the AVL and why we need the balanced binary trees. Okay, so let's dive into code, and after that we will simulate the rotations on our perspective. So new share Visual Studio. Okay, so let's skip the init part. Okay, so include standard input output. Okay, include malloc, and I will go for a basic tree. So we play with structures. Let's not use that. I will write the information directly in the node. Okay, so this is the binary search tree node, and like I said, it has the same structure for AVL or normal binary search tree because they are still binary trees. Okay, so I start with the right link and the left one. Okay, so pointer to the left one. Okay, and for value you can add any value, but let's store only the keys. And here you can attach your data structure. Okay, you can define your own data structure. So this is the key, okay, of the binary search tree node. And we know it's an AVL because we will take care of this tree. But in terms of structure, there is no difference. Okay, so an AVL tree doesn't have a different structure. They are the same. Okay, so we have the structure of a binary search tree node. Let's we need this function to initialize it. Okay, so binary search tree node asterisk init node, and here we need only the key. Okay, in key. So here I will have a binary search tree node pointer. Okay, new node equals binary search tree node asterisk malloc and the size of binary search tree node. Okay, don't forget to initialize. We had this issue on Tuesday. So new node left equals null and new node right equals null. Okay, so this is how we initialize a node. Now, what else do we need? Now, in order to print the
key,
yeah,
and to return it.
Yeah. New node. I simplified it too much. So yeah, okay, key. Okay, and return new node. Okay. Now, what else do we need? We need to print the tree in, I will not choose or we can copy paste. So let's print the tree in order to check it later. So we want to print the key, the binary search tree. So this is a method for print tree, and let's say this is in order. And here you need the root node, bst, okay, root. And if the root doesn't exist, we stop. So we do a recursive processing. And in order means always check go on the left side, print the key when you came back, and after that follow the right path. So if root different than null, or just if root, because null is 0. Okay, now we print the tree, in order by following the left side. Okay, when we came back from this recursive call, we print the key. So printf %d, and here I have root key. And after that, we follow the other side, print 3 in order, which is root right. Okay, so this is in order. Okay, and here just return. Okay, because there is nowhere to go. We hit a dead end. Now, if you want to do the other printing, so this is in order. For example, you want pre-order, it's easy. If you know one, you know all the others. So this is pre-order. The only difference here is that for pre-order, you print the key and after that you follow left, right. Okay, so this is pre-order. It's the same, you just change the location of printf regarding continuing on left and right side. Okay, so we know how to create a node, we know how to print the tree. Now, what we really need is a function that will give us the height of a tree or a subtree. So we need to find this height, okay? And this is a function that we needed here because you see each time when we check if the tree is still balanced or unbalanced, we do this subtraction. Height of the right side subtree minus height of the left side subtree. So if you give me a node, we need to be able to compute its height. Okay, so let's do that. So this is a function for computing the height. So this function generally returns an integer. So it's called get tree height. Okay, and here we need the root node of that tree. But any node will be used in order to compute the height of subtrees. Okay, now this is another recursive methods, and I already said that to you. All the methods here are recursive. Okay, and you always need to think to imagine how recursion works, because this is the fireman bucket line. Okay, so you have a lot of firemen and they pass the bucket to each other. Okay, the bucket goes where the fire is, they use the water, and after that the bucket goes back. Okay, so when you do a recursive call, okay, you are here, and after that you do another recursive call on the right side and another one on the right side. At some point you reach here, and at this point you will go back. So you need to imagine that in a recursion, the execution will follow a path, and after that it will return on the same path. And we need to use this in our advantage. So for example, how can we count how many we are here in this group? Okay, so for example, if I have an image over the entire group, I open the Zoom participants list and I will count how many we are. And this is one way of doing. But if somehow you relay the Zoom session to the other ones, so I see only one of you, and that person will retransmit the Zoom session to another colleague, and that colleague to another student, and so on. So each of you will see only one person, okay, not all of them. How can we count how many we are in the same Zoom session? And if I will do a recursive call, it will be like this. I will ask you, so you are my only contact person, and I will ask you, how many of us we are here? And now you'll say, I don't know, but I have a contact. Let me ask that person, how many of us we are here? And this question will go by each of us until the student, which is the last one. Okay, is the last one in the row. There is no one behind him. So at that moment, he gets this question, how many of us we are? He looks backwards, and if he say, or she says, we are only one, because it's me. There is no one after me. So we are one. And now the answer goes backwards to the initial person that started this query. So the last person responds with, we are one, because this is me. The person that gets the answer now says, okay, so after me, there is only one person, but with me, we are two. And now this goes back to the previous person. So it's 2 plus 1 plus plus plus. And in the end, the answer, this computed answer will get back to me. Let's say the answer will be 16. And I will say, okay, 16 plus me. So we are 17. So this is how recursion works. And you need to use this in your favor. So this is like throwing a ball, and you have a dog that will always bring back the ball. So I don't know, you use that ball to hit something, and you have your dog, which will always bring the ball back to you, okay? So let's use this one. So how I will write this get tree height. So for example, always start with the last person. Always think that at some point, someone will get there, okay, to the last person. And the last person will ask the next to him, but there is no one there. So this is the case, okay? The call gets to the last node, and the last node will try to ask this question on the right or left, and you will hit a dead end. So if root equals null, so if you hit a dead end, what will be your answer? Return 0, okay? So we are here. That's the tree height. There is nothing here. There is no levels here. Okay. Now, what's happening if the root exists? Okay. And you see, when we compute the tree height, I think it's better to start with another function just to help you see the recursion. Let's just leave this for a moment. Let's write another function. Get nodes count. Okay, because here it will be easier to see how recursion works. And after that, for height, there is a catch. We don't need to count. We need to count the levels. So get nodes count. So if we reach a dead end, there is no node there, but else it means we are on a node. Okay, root is not null. So my answer here will be return 1 plus, so this is me, the 1, plus what? Plus the number of nodes that I have on my left side and the number of nodes that I have on my right side. So get nodes count on my right or left side, it doesn't matter. In the end, it will traverse both sides, right? Plus get nodes, nodes count on root left. Okay, so this is how you count how many nodes there are in a tree. You see, each node will say count me plus what I have on my right and my left side. So this will go recursively through the entire tree. When you will hit dead ends, so for example, the current node right, it's null, you will go there, that will return 0. So it'll be 1 plus 0 plus whatever you have on left side. So this is how you count the number of nodes in a tree. Now, what we want to count is the height. So remember, the height is not how many nodes you have on a side, it's actually how many levels, you see? So the height of this tree, okay, is what? Is 1, 2, okay? If we don't count the current node, or maybe it's 3 if you count also the root node. So let's say it's 1 level, 2 levels, 3 levels, okay? Now, what's the height of the entire tree here? 1, 2, 3, 4, okay? So this is the height. Okay, so how we compute the height in a recursive manner? Now, the height here needs to count how many levels we go downwards, okay? Not how many nodes we have on left or right subtree. So when we are here, we count this level, it's 1 plus, so we are on the level. And now when we go on this side, if we add 1 to this one, and if we go on the right side and after that on the left side, we need to know if we are on the same level. So let's be smart about that. What's the information that we can use to know we are on a level? Okay, so we are here. We went downwards. How do we know where, if we go downwards? We know because this function will be called again. So this function is always called when we go downwards. Okay. And then.
I don't think we can use nodes count.
Sorry?
I don't think we can use nodes count.
Yeah, but nodes count will just say, it's similar with nodes count. I'm thinking about this, but it's not that, because that will count how many nodes you have, and the height of a tree is not directly, let's say, because it's not perfectly balanced, so we can't determine the height based on the number of nodes.
Yeah.
We need to count each time we go downwards. Okay, yes, I know. So how do we do that? Is by counting actually the level here, okay, passing the current level downwards. So each node will check what its level. Okay, so what I want to say is this one. So we are here, right? We count this as level 1. So we have 1 plus what? Now, when you do a recursive call here, this node will get this one from here, okay? And now, because we went downwards, now the number of levels should be 2. But when you are here and do another call on the right side, once again, you get the current level from here, which is 1. This will add 2. Okay, so they are both now 1 and 2. And so there are 2. Now this will go to 3, 3, 3, and 4. And now this 4 goes backwards. So it's actually a function that will determine the max between two values that we receive either from the left or either from the right. So we count each time downwards, we get the response, and we compute the maximum. Okay, so we are here. We are on level 1. Okay, so it's 1 plus what? We know that after that we count the height of this side and the height of this side. So in the end, the height of the entire tree is 1, the current level, plus the maximum between the height here and the height here. Because you see, this is the height. It's the maximum between these two heights here, left or right side. And here you will have 3 as a response, and here you have only 2, the height. So in that way, the height will be maximum between 3 and 2. So in that case, it's 3 plus 1 is 4. Okay, so if I go back here, we need this function, maximum between two values. Max int a int b. Okay, so here I have return if a greater than b. This is the question. Return a, otherwise return b. Now, if they are equal, it doesn't matter. They are both the maximum. Okay, sometimes they are equal. So else here, so if you hit null, it's 0. So else, it's actually return 1. It's the current level. I'm on a level, so I know that, plus maximum between what I get from get tree height on my left or right side, it doesn't matter, root left, and the value on the other side, get tree height, root right. Okay, that's why I said earlier it's similar, but it's not the same. So here, this is actually counting how many times we call the same function going downwards. So you see, each time we enter a level where that node is different than null, you already know you are on a level inside that tree. So from this point on, you want to see how many times you go downwards on the left side or on the right side. And the maximum between these two numbers will actually give you the height at that point. And after that, you add 1 because you are on a level and you return this value. Okay, so this will get up backwards and compute the height. Let's test this. So if I go back here, let's see, I will call here get tree height, and we are here. So let's try to clean a little bit this part here. Okay, and I will write the values on this side. Okay, so we call it here to check the recursion. Okay, so we call it here. The first time this recursive function will be called, you will have 1 plus max between the values, the height, the recursive call on left, or let's see, on left and right. Okay, so now this call here waits for the value here and the value here in order to determine the max. And now we go on the left side. Now, once again, the call finds a node. So here we have 1 plus. Once again, here we have max between two values, but we don't have the values yet because we need to do a recursive call on left and right. So once again, we wait for the values. So we continue on left. Here on left, we have 1 plus max, the same max between two values. You don't have the two values yet. You continue to the left, and here we have 1 plus max between two values. And now we continue on the left side. It's if root is null, so return 0. So now we have a value here. And now we continue on the right side. Once again, it's an empty node, it's a null node, return 0. So in the end, we find a function that now will terminate. So we have what? 1 plus max between 0 and 0. This is 1 plus 0. So this function will return here 1. So we have a value for this max. Now we continue on the right side. Now on the right side, there is nothing. So here you'll have if that node exists, it doesn't exist, return 0. So we have the second value for max here. So now we have another function that terminates. It's 1 plus max between 1 and 0. So this function will return here 2. So you have this value here, 2. Now you continue on the right side, it's 0. So you get a 0 here, another function that terminates. So you have 1 plus max between 2 and 0. So it's 1 plus 2. So this returns 3. So we have a value here, 3. And now we need to continue to wait for the right side to be executed. Okay, so in the end, I think here, after all these topics, you will see 2. So the height of the tree will be 1 plus max between 3 and 2 is 3. So 1 plus 3 is 4. Okay, so this is how we compute the height of a tree. Now, let's do the balance factor. So int get balance factor of a node, whatever, a node. Okay, it could be the root, but it's just a node. So what do we do here is return. Let's do right minus left or whatever, it doesn't matter. So you can choose the direction. So here I will do what? Return get tree height of the right side minus get tree height of a node left side. Okay, so this is the balance factor for any node. So what do we need to do now? We need to insert values in a binary search tree. Let's do a compile, not wait for to write the entire solution. So build, rebuild. Okay, so from my perspective, it's okay. We will test the methods, but right now we don't have something to test. So let's do the insert function. And we will use the approach from Tuesday because recursively it's more efficient to write it. Okay, the one that each time returns the current node. So binary search tree node insert. And here you have the binary search tree node root. So, and the key, int key. Let's create the new node if the current node doesn't exist. So if root equals null, return init node of key. Okay, else it's a binary search tree, so you need to check if root key equals key. We don't accept it, so in this case return, and we don't want to break the tree, return root. Okay, and in this case is like is a duplicate. Okay, now like I said, I think it's the first time I write this if else. Let's not write it. Okay, and else if root key greater than key, it means we need to find the location for this one on the left side, so it's greater than the key. Okay, so here you have root equals insert of root left, and else is the same but insert of on right. And the key, each time the key, I forgot it. So this is actually the insert in a binary search tree. Obviously, if we leave this as it is now, we will have a problem because we will unbalance the tree. So we can insert 10, 20, 30, 40, 50, and you will have a tree which is unbalanced. So let's test these methods. Binary search tree node root equals insert. Yeah, I need to start with, or we can do that. Why not? Insert into null, because we don't have it. Okay, and after that you have the key, let's say 10. And after that I will write root equals root, sorry, insert into root 20. Let's duplicate the keys. So we will test with this one, 40, 50, and another one, 100. So now the tree will be unbalanced. It's like a simple linked list. Let's print it. Okay, so printf \n the tree is. Now I will print it in print tree in order. Okay, because in pre-order you will get the value sorted. So maybe in tree in order we see the relation. So root. Okay, so now we have a tree, and let's print the height. That will be interesting. So printf \n the tree height is %d, and here I will have get tree height of root, and also how many nodes. Nodes count is get nodes count. Okay, so let's rebuild, and let's test it. So what values should we get here? So for height, because the tree is on a diagonal, so the height will be actually equal here. It's 1, 2, 3, 4, 5. Okay, and the nodes count, it's still 5. But remember, I choose the values in a sorted manner just to show you that an AVL will fix that for us. So here it's a normal binary search tree. So Control F5. Okay. And I have an issue here. Is only 1. So again, like on Tuesday, I'm losing the root node, and it's here in insert. So let's see, if root equals null, return init node. If root key equals key, return root. If root key, sorry, my mistake, equals, sorry, not key, it's left, because we break the links here, and that's why you have only 1 node. Right. Okay, and I did the same mistake on Tuesday. Like I said, I don't memorize these examples. If I will reach that point, I will choose another thing to do. Maybe I will hire as a programmer, but until then, I will not memorize them. Okay, and that's why sometimes I do mistake, but in this way, I can show you mistakes. And this is one scope that I have. Okay, so please fix this part here. Okay, you have seen the symptoms. We had only 1 node. It's like each time you inserted a new node, that node was the only one. Let's try again. Control F5. Okay, the same problem. The tree is 100. Okay, let's check the problem again. So root left equals insert. Okay, yeah, we don't return here. I think this is the problem. So if root key root left becomes insert, okay, and we don't return, because you see, we assume that we return on each branch a node, and here we don't return. We just get a value from the next call, but we don't return root. Or I think instead of doing this return each time, return root. Okay. What error? Oh, okay, just a glitch. Okay, so if root key return the root, it's a duplicate, else go on left and right, and after that return the root. Now I think we can combine these two into one, because we return the same value here. Okay, let's see this again. Control F5. Okay, and now we have it. So the tree is 10, 20, 40, 50, 100. The tree height is 5. The nodes count is 5. Now, this was pre-order. So pre-order means key left, right, key left, right, key left, right. And if you traverse it, you will see it's 10, 20, 40, 50, 100. Okay, so if you didn't have the chance to fix it, this is the final version of insert. Okay, so the idea is to return each time the current node, because otherwise root left at some point will receive something from the next insert, and maybe this is the other call, you will get a new node. But after this point, when you go back towards the initial root of your tree, root left equals what? Equals nothing. Now, I think in Java here, if you forget this return, you'll get a compiler error. And that's a great thing, because it will remind you that you have branches that they are not returning a value, and you should. Okay. Okay, so this is the insert, and we have the functions, the auxiliary functions to compute the balance factor and the tree height. We can also count the nodes, but this is additional. Okay, so let's see. In order to rebalance the tree, you see, when we get back from the location when we inserted the node and we go back, okay, each time we need to recompute the balance factor for the current node. Okay, so insert will call here on left, on right, and after that you get it back. So let's try to visualize this. I will open some brackets here, because here we need to check the balance of our nodes. So after you did the insert, we will do this int balance factor, or balance, equals get balance factor of root. Okay, and let's print this one. Printf the balance factor for %d is %d. So here I want to print the key and the balance factor. And because I think we want to do this also here, okay, once again, let's write this only once here. Yeah, sorry for that, because in the end is the same root, so it's the same value. Okay, just leave the brackets, maybe we will need them later. Now if I run the same example again, each time we insert a new node, the balance factor will be computed when we go backwards. How do we know we go backwards? Because you see, I'm computing the balance factor after we returned from insert. Okay, so this has been executed. We are back on the current node. We are just preparing to exit from this current call of insert, and now we recompute this. So let's see these values, and in order to see them, I will add here this printf, because otherwise you'll see a lot of numbers. Okay, just to focus on each insert in order to see what were the balance factors after each insert. Okay, so if I run the example again, Control F5. Okay, here are the values. So yeah, I forgot about the backslash n. Sorry, let's I have a backslash n here. We needed another backslash n because printf print3 does not add a printf. So let's fix that to see them on the same line. Sorry, I will just close this. Okay, so print3 in order. Let's see, print3 in order. Yeah, I will add. Yeah, but I have just a moment. Let's see. What was the issue? Okay, the balance. Okay, I think the problem is here. Yeah, here is the problem. Okay, just add backslash n here. The balance factor for is okay. And now they will look more, I hope, more clear. Yes. So let's see. You see, we inserted 10. This was the first node in the binary search tree. Now, what was the after you inserted 10 and you have a tree with only one node? What's the balance factor for 10? Is 1. Why is 1? Because he is on level 1. Okay, on the right side and on the left side he has nothing, so its height is 1 because it's a single node. It's a tree with a single node. Now we inserted 20. You see, 20 balance factor is 1, and the balance factor now for 10 after we inserted 20, and remember 20 is on the right side because it's bigger. Now the balance factor for 10 is 2, which means the height of the right subtree is bigger than the height of the left subtree, and the entire height of the tree is 2. It's the node itself, 10, and its right sibling. So you have 2 levels, so it's 2. Now we inserted 40. The balance factor for 40 is 1. The balance factor for 20 is 2. And now you see for 10 is 3. And this is the location where our tree has become unbalanced, here. Okay, because like I said, in a AVL tree, or an AVL binary search tree, we accept values, and I said either -1 or 1 or 0, but here we have 1, 2, and 3. Now, in order to change that to 1, 2, and 3, we can do a change here in the tree height. Okay, so here it's return 1, get tree height. So we have it always with 1, 2, 3. Okay, yeah, let's leave it like this one. 1, 2, 3. Okay, let's run it again. So in this case, if we count the current level, let's say the accepted values for balance factor will be 1 and 2. Okay, I will run it again. And 3 means it's already unbalanced. So Control F5, Control F5. Okay, so this is the location where the tree has been unbalanced because it's 1, 2, 3, and now it's continuing to be unbalanced, 1, 2, 3, 4. So let's check this situation, why it's unbalanced. So if I go back to the drawing board, okay, let's clear the canvas. Clear canvas. Okay, it means we are in this situation. We had it 10, after that 20, and after that 30 or 40. Sorry, it was 40. Okay, so we have this tree, and here the height of this tree is 1. The height of this tree is 2. Why 2? Because it's 1, the current level, plus maximum between the height of the right side and the left side. So the height here is 2. Now, what's the height of this, or the balance factor here? It's 3, because the height of the entire tree is what? Is 3. Why? Because you have 1, 2, 3, yes, minus nothing on this side, so it's the maximum, so it's 3. Okay, now we said that we accept only these values, 1 and 2. And at this point, if you see this tree, it means this node will be a pivot for a rebalancing, which means, so this is a pivot. And because the value here is positive, it means, and also it's sibling on the direction of the unbalance is still positive. You see, it's 3, 2. It means the entire tree is unbalanced on the right side. So at this moment, on this pivot, we need to do this rotation. And you see, because the value here is positive, it means the tree is unbalanced on the right side. And here we do a rotation to the left side, which is the opposite of the unbalanced direction. Now, if you have another tree, for example, you have 10, and here you have 7, and here you have 5. If you compute the balances here, so the balance factor for this one is 1. The balance factor for this one will be minus, let's see. So the height of the right side subtree is 0. The height of the left side subtree is 1. 0 minus 1. So will be, and it's always counting this current level here. Okay, so this will be, that's interesting.
Isn't with minus?
Yeah.
It's -1, -2, and -3?
It should be -2. Okay.
Yeah, and
this
you,
one -3. Okay.
yeah, you put it by mistake, I think. The balance factor 1 at the last
here.
node.
Yeah.
Yeah, that was the issue.
Okay. let's, yeah, that's why it was distracted. So let's test with this node. This is interesting. Let's see. If I run again the example with 10, let's see, 9, 5, 3, and 2. So this will go on left side. Let's run it. Control F5. Yeah, it's okay. You see, now it's -1, -1, -2, -1, -2, -3. So in this case, if the values are negative, it means you have an unbalance on the left side, because we always do right minus left. So in this case, once again, because the unbalance is on the same direction here and here, how do I know? Both balance factors here and here are negative, or they are positive. It means, once again, that this can be easily solved by rotating the pivot in the opposite direction. So here the unbalance is to the left. So we do a simple rotation on the right. So after we insert a value, when we go backwards, we check the balance factors for nodes. And we just did that. And the first node that we encounter with either 3 or -3, it's the first node that we need to rebalance. Okay, we don't leave anyone behind. You don't reach the root until you solve all these issues. Okay, and these are the cases for simple rotations. How do I know it's a simple rotation? If I find the balance factor of -3 of a pivot, I will always check the left sibling. Okay, and this is obviously the unbalance is on left side because it's a negative value. And if the left child of this one has a negative balance factor, it means they are on the same direction. So the rebalancing is done with a simple rotation. And in mirror is the same story on the right side. Okay, so if I go back to the source code here, this is where we need to check. So the balance factor is, and these are the cases when we need to do. So if you find a node, so if the current node has a balance factor of -3 or +3, it could have not 4 or -4. Why? Because if you reach a node where you have -4 or 4, it means you did a previous insert and you didn't rebalance the tree. Remember, an AVL, it's a tree in which always all the nodes have a balanced tree of either -1 or -2. Okay, you can't have -3. If you leave a -3 and later you get to a -4 or a 3 and get to a 4, it means at some point you did an insertion, but you didn't rebalance the tree. Okay, so you can't get to that. So let's check the situations. If balance equals -3, now we need to be sure that this is we need here a simple rotation. So check the unbalance of the left sibling. Okay, so if balance equals -3, now if get balance factor of root left is negative, is less than 0, okay, it's still negative. It could be -2, but let's say it's negative. In this case, we do a simple rotation to the left, to the right, on the current node, and it's called a pivot on the current node. Okay, now what will happen if the balance factor of your left child is not negative? And this are the the situations where you need to do a double rotation. So for example, let's clear the canvas and show you that case. So we are on a negative situation. Just a moment. So we are like this. You have a node here, this has a node here, and now this has a node here. Okay, you see this is +1, this is -2. Sorry, this is +1, this is +2, and this is -3. Okay, you see the value of the sibling here, because it's a negative value, we have an unbalance on the left side. So I check the left sibling, but it has a positive unbalance, which means it's unbalanced on the other side. So in this case, how do you fix this one? Because a simple rotation will not help you. So in this case, you do on the child a simple rotation on the same direction of your pivot unbalance. So here you do a rotation to the left. Now, what do you get out of this one? You get a node here, you get another node here, and now you get a node here. If you recompute, the balance factors are -3, -2, and -1. And after that, you do a rotation here in the initial pivot on the opposite direction, to the right. So in the end, you get to this node, this node, and this node. So you see, these combinations of the pivot is unbalanced on one direction, but its child on that direction is unbalanced on the opposite direction, are actually solved by applying a double rotation, a rotation on its sibling, and after that, the normal rotation on the pivot. And this goes also for the mirror scenario where you have it on the right side. Okay, so if I go back here, so if get balance factor is less than 0, now else means we do a double rotation. Okay, and you have the details. Now, if the balance is, they could be in the same time -3 or +3. So it's either -3 or +3. So if balance is 3, check the balance of the right sibling. Okay, get balance factor of right. And if this one is positive, they are unbalanced on the right, we do a simple rotation to the left on the current node. Now, otherwise, so you see the pivot is unbalanced on the right, but the sibling on the right is unbalanced to the left. Once again, you do a double rotation. Now, how do we do a rotation? Okay, so how do we rotate the current node? So what means a double rotation? So a double rotation, oh, sorry, a simple rotation. So let's suppose we are here, and this is our root node. Okay, in this case here, -3, -2, -1. How do we rotate it? So in this case, the rotation, because here you may have links, possible links here and here. Okay, so you may have a rotation, a link here. I will choose another color. And maybe you have another link here. How do we rotate them? Let's see. If this node goes downwards, you see this node here, it will actually become the, let's clear the canvas. Because if you understand the story, it's quite simple. So we have this case. Okay, so we need to do a rotation here. Okay, like this on this side. Now, we may have here a possible link, and also we may have here a possible link. But the main actors of this rotation is this one here and this one. So what is happening? If you rotate this one here, if this node goes on the right side of its left sibling, what will happen with the child, the, let's say, right child of this one here. So I will note this one right child, and this one I will call it R. So this is R child and R. Now, if this goes downwards, okay, R is still preserved, and this node here will have this link available, okay, because you break this link here, and this one here will be available. Now, what's happening with all the nodes here? Now, let's think for a moment. What's the relation between all the values here and this node? All these values are greater than this value here from the key here. How are all these values regarding this node? They are all less than that. So what will happen when you do the rotation? So let's say this is X, this is Y. Now Y will be here. It still have its initial sibling here. This is not affected anyway. What's happening with the right child? Now on its right link, you'll have X. So X goes here. What's happening with its initial right? It's still here. This has not been affected. And this child here, the right child, goes here. And if you check the values, this is still a binary search tree. Okay, so a simple rotation to the right here will mean what? The right link of the left sibling of Y takes the value of X, you see it here, and this child here, the right link, the right pointer of Y, is used to initialize the left pointer of X. Okay, so if you draw them, it will be very clear how the values are changed. So let's write this rotation. So I need to write it here before insert. So this is a simple, yeah, I will name the function. Now, what is happening? The root node or the current node is changed. Okay, you see in the drawing. So the current node is changed. So we need to return to its parent the new sibling here. Okay, because if this node has a parent on any side, for example, this side, now you need to return Y in order to make the parent of X now to point on that link on Y. But remember, in insert, each time we return the current node. And in insert, we always write this. You see, root right equals insert, root left equals insert. So if we do a rotation inside an insert and we return Y, the link will be reinitialized. So this will go perfectly. We don't need to do anything extra. So let's write this function. BST node. Okay, so simple right rotation. So what do we get here? We get the pivot. Okay, we know it's a simple right rotation, so we don't check. You do the check here. Okay, so you already know you can do a simple right rotation. We don't check, we don't validate again. So accordingly with the drawing, this will happen. The left sibling, and I can get, let's get a pointer to it in order to do that in multiple steps. And so I will do a BST node, and let's say this is left sibling equals pivot left. So we have it. Okay, and let's see what's happening. The first relation that I will break will be this one, because I already have the left sibling. So I will say pivot left equals with left sibling right. You see, I do this, X left now has the right child of Y. So new share. So pivot, and we already saved the left sibling. Okay, so pivot left equals left sibling right. Now, if that's a null pointer, it's null. Okay, no one will be upset about that. And now the left sibling right becomes the pivot. Okay, return left sibling, because this will take place of the initial pivot. So this is a simple right rotation, and the other one will go in mirror. So this will be a simple left rotation. Okay, so here you will take the right sibling, pivot right. Now pivot right gets the right sibling right, no, left. Okay, and right sibling right, let's see, no, left, because we already saved that, is pivot. And now I will check this on a drawing before uploading on Git. Okay, so these are the two simple rotations. Now what you need to do is to do the double rotation, which is actually a combination of a simple rotation on the child to the opposite direction of the unbalanced, and after that the simple rotation. Okay, but the double rotations are actually based on calling simple right rotation on different siblings. And this is it. You call these functions here. Okay, so for example, here we do a simple rotation to the left on the current node. Okay, which means here we return, because I want to return the new root. So here it's a return simple left rotation on root. Okay, and here you do a simple rotation return simple right rotation on root. Okay, so these are the this is the AVL. I will check cross check before uploading on Git, just to be sure not to give you a bug here, the simple left rotation. But in order to finish the example, unfortunately we need to stop here because I had another course at a master program. So the only thing that you need to add here are the double rotations, and you need to call them here, okay, on the insert. And like I said, double rotations are based on these two simple rotations.
Can I have a quick question?
Yeah.
So when we compute the tree height,
Yes.
don't we have a linear complexity, so we kind of defeat the purpose?
What's the linear complexity of what? You mean by going through all the nodes?
Yeah.
Yeah. So computing the tree height will go through all the through all the nodes. Yeah. And this is also a complexity n has get nodes count. It's the same. They have both the same complexity. Yeah. So here, but remember, the purpose of the binary search trees are to give you the best performance on search, not on insert.
Okay.
So you build it, and after that you use it for search. And like I said, they were built only for this operation, to give you the fastest response on search. Now anything else, they're not so perfect. So yeah. But let's suppose you do less inserts and more searches, and generally that will be the case. Yeah. So yeah, it has a complexity n. But no one says that all binary searches will have the same logarithm based 2 out of n for all operations. It's only for search.